We have a sphere of radius 2 meters that has a uniform charge density of 3 coulombs per cubic meter, and we want to find the electric flux density field everywhere. This charge distribution has a great deal of symmetry, spherical symmetry, so we can apply Gauss's law to quickly find the electric flux density field everywhere. As always, begin by drawing a figure of the problem. Here is our sphere of radius 2 meters, and this spherical region has a uniform charge density of 3 coulombs per meter cubed. If you place a test charge anywhere, it will experience a force only in the radial direction. And that would be true whether the test charge was somewhere inside the distribution or outside the distribution of charge. The force will vary with the distance you are from the charge distribution, but it will not vary if you move in the theta or the phi direction. The electric flux density field, therefore, only has a component in the radial direction, and it only depends on R. The Gaussian surface that will match the symmetry of our electric flux density field will be a sphere. You'll have to apply Gauss's law in two regions. The first region is when the radius of your Gaussian surface is less than 2 meters, and the other region is when the radius of the Gaussian surface is greater than 2 meters. When the radius of the Gaussian surface is less than 2 meters, it's always inside your charge distribution. When the radius of the Gaussian surface is greater than 2 meters, your charge distribution is always inside your Gaussian surface. Let's first look at region 1 when the radius of the Gaussian surface is less than 2 meters and apply Gauss's law. We substitute in the form of our electric flux density field and the value of our volume charge density. The electric flux density field is constant on the surface of our Gaussian surface, so we can move it to the left of the integral sign, and the unit vector in the r direction dotted with our surface differential gives us the surface differential in the r direction. Since the charge density is uniform inside our Gaussian surface, it can be moved to the left of the integral, so then we're just integrating dv, which will give us the volume of our Gaussian surface, 4/3 pi r cubed. The integral of ds sub r over the surface of our Gaussian surface is just the surface area of that sphere, which is 4 pi r squared. The 3's cancel, the 4 pi's cancel, and an r squared cancel from each side. When you put r in meters, you'll end up with coulombs per meter squared, so the electric flux density field for r less than 2 meters is r coulombs per meter squared. Now let's look at the region when r of our Gaussian surface is greater than 2 meters. Nothing will change on the left side of Gauss's law. The right side is going to change because the charge inside our Gaussian surface will always be the same. It will be the total charge on our sphere. So this r here will not be a variable. It will become the radius of our charge distribution, 2 meters. So since r has become 2 meters, you won't get the cancellation of an r squared from each side. So let's change this to 2 meters cubed and retain the r squared on the left-hand side. The 4 pi's will still cancel and the 3's will cancel. The charge enclosed will always be 8 coulombs, the total charge on our sphere. Solving for our electric flux density field, we get 8 over r squared, and that will be coulombs per meter squared when you put r in meters. Combining this result for r greater than 2 meters with our previous result for r less than 2 meters, we have our electric flux density field everywhere.